this video, you'll learn the basics of string theory and what comes beyond it. We'll talk about why string theory is even needed in the first place, and whether it explains anything that traditional atomic theory can't. We'll explore what strings are actually made of, and whether anything can be more fundamental than strings themselves. We'll also dive into some of the wild ideas and theories connected to string theory. Let's get started. Imagine for a moment that you're holding a single thread between your fingers. You can feel its texture, its weight, its reality. Now, I want you to imagine something almost impossible to comprehend. Imagine that this thread becomes smaller and smaller and smaller. It shrinks down past the width of a human hair, past the size of a grain of sand, past even the tiniest speck of dust you could see under a microscope. It keeps shrinking until it becomes so incredibly small that if you took a billion of these threads and laid them side by side, they would stretch across a distance smaller than the width of a single atom. According to a revolutionary idea in physics called string theory, these impossibly tiny threads are what make up absolutely everything in our universe. Every atom in your body, every particle of light streaming from the sun, every bit of matter and energy that exists is made from these fundamental strings. But here is where things become truly mysterious, and this mystery is what will guide our entire journey today. If these strings are the most fundamental things in existence, if they are the ultimate building blocks from which everything else is constructed, then we have to ask ourselves a question that sounds simple, but leads us into some of the strangest territory in all of science. What are these strings made of? This question has puzzled some of the brightest minds in physics for decades. It is a question that will take us on an extraordinary journey through ideas that challenge everything we think we know about matter, space, time, and the very nature of reality itself. By the end of our exploration, you will understand why this simple question reveals something profound about the universe we live in. The problem with breaking things. Apart, human beings have always been curious creatures. Throughout our entire history, we have tried to understand the world around us by taking things apart and looking at what is inside. This instinct to break things down into smaller pieces has driven some of our greatest discoveries. The ancient Greeks, more than 2,000 years ago, sat in their schools and wondered about this very question. They asked themselves, what would happen if you took a piece of matter, any piece of matter at all, and you kept cutting it in half? You cut it once, then you cut each piece in half again, then again and again, over and over. Would this process go on forever? Could you keep dividing matter into smaller and smaller pieces without end? Or would you eventually reach a point where you could not cut any further, where you would arrive at something so fundamental that it could not be divided anymore? The Greek philosopher Democritus believed you would eventually reach these uncuttable pieces, and he gave them a name that has echoed through history. He called them atoms, which in ancient Greek literally means that which cannot be cut. For more than 2,000 years, this remained purely a philosophical idea, something people debated in universities and thought about during long contemplative walks, but nothing that could be proven or tested. Then something remarkable happened in the early 1800s. Scientists began to discover that atoms were not just abstract philosophy, but real physical objects. Through careful experiments with chemistry and the behavior of gases, scientists proved that matter truly was made of these discrete units that Democritus had imagined so long ago. For a while, everything seemed to make perfect sense. We had found the fundamental building blocks of nature. The periodic table organized all the different types of atoms into a beautiful system. Chemistry could be understood as atoms, combining and recombining in different ways. It appeared that we had reached the end of the journey that the ancient Greeks had started. We had found the atoms, the uncuttable things, and the mystery was solved. But then something unexpected happened, something that would change everything. As scientists developed more sophisticated tools to probe the nature of atoms, they made a shocking discovery. Atoms were not uncuttable after all. They were not the end of the line. Each atom, it turned out, had structure inside of it. At the center of every atom was a tiny dense core called the nucleus, and orbiting around this nucleus were even smaller particles called electrons. This discovery opened up an entirely new world of questions. If atoms had parts, then what were those parts made of? Scientists looked even closer, developing more powerful microscopes and particle accelerators that could smash atoms apart to see what was inside. They discovered that the nucleus itself was made of two different kinds of particles. There were particles called protons, which carried a positive electric charge, and particles called neutrons, which had no charge at all. But the story did not end there either. As scientists built even more powerful machines and conducted even more sophisticated experiments, they found yet another layer. Those protons and neutrons were themselves made of smaller particles called quarks. It was like opening a set of nested boxes, where each box you opened contained another smaller box inside, and that box contained yet another box over and over again. By the middle of the 20th century, physicists had catalogued not just a few of these fundamental particles, but dozens of them. There were 6 different types of quarks with whimsical names like UP and down, strange and charm, top and bottom. There were electrons and their heavier cousins called muons and tau particles. There were ghostly particles called neutrinos that could pass through solid matter as if it were not even there. There were particles that carried forces like photons for light and gluons for the force that holds atomic nuclei together. The situation had become incredibly complicated. Each time scientists thought they had reached the fundamental level, they discovered more layers beneath. It was starting to feel like this process might go on forever, that perhaps there was no true bottom to reality, just an endless series of smaller and smaller structures disappearing into an abyss of infinite complexity. Why we needed string theory. By the middle of the 20th century, physicists found themselves in a frustrating situation. They had discovered this bewildering zoo of different particles, each one behaving according to its own set of rules, each one seeming arbitrary and disconnected from the others. It was as if they had collected books from a vast library, but every single book was written in a completely different language, with no dictionary to translate between them and no underlying grammar that connected them all together. Scientists are driven by a deep belief that nature should be simple and elegant at its core. When Isaac Newton discovered that the same force that makes an apple fall from a tree also keeps the moon orbiting the Earth, it was a profound unification. When James Clerk Maxwell showed that electricity and magnetism were two aspects of the same electromagnetic force, it was another beautiful simplification. Physicists began to wonder if there might be some deeper principle that could explain all these different particles, some underlying unity that would show they were all manifestations of the same fundamental thing. But there was an even more pressing problem that was keeping physicists awake at night, a problem that threatened to shake the very foundations of physics. We had developed two incredibly successful theories about how nature works, but these two theories were completely incompatible with each other. It was as if we had discovered that nature spoke two entirely different languages that could not be reconciled. The first theory was general relativity, developed by Albert Einstein in 1915. This theory explained gravity and how it works. Einstein showed that what we experience as the force of gravity is actually a warping of space and time caused by massive objects. Imagine space as a rubber sheet stretched flat. When you place a heavy ball on the sheet, it creates a depression, a curve in the fabric. Smaller objects roll toward the heavy ball, not because of some mysterious force reaching out and pulling them, but because they are following the curved contours of the sheet itself. This theory explained the behavior of planets, stars, galaxies, and even the structure of the universe as a whole with stunning accuracy. The second theory was quantum mechanics, developed by many scientists in the early 20th century. This theory explained the behavior of tiny particles like atoms and electrons. Quantum mechanics revealed that at very small scales, reality works in fundamentally different ways than our everyday experience. Particles can act like waves. They can exist in multiple states simultaneously until they are observed. They can tunnel through barriers that should be impossible to cross. Energy comes in discrete packets rather than smooth, continuous amounts. Despite how bizarre these ideas seem, quantum mechanics has been tested more thoroughly than perhaps any theory in the history of science, and it has passed every test with flying colours. Here was the problem. Both of these theories work brilliantly in their own domains. General relativity explained the cosmos with remarkable precision. Quantum mechanics explained the atomic world with equal success. But when physicists tried to apply both theories to the same situation, when they tried to describe what happens in regions that are both very small and involve very strong gravity, the mathematics completely broke down. The equations produced nonsensical answers. Numbers would blow up to infinity. The calculations would spit out results that made no physical sense whatsoever. It was as if you had two maps of the same territory, and when you tried to overlay them, they did not match up at all. Roads that should connect did not line up. Rivers flowed in opposite directions. The two maps seemed to be describing completely different worlds. This problem became especially acute When physicists tried to understand situations like the Big Bang that created our universe, or the centers of black holes, where gravity becomes so strong that it crushes matter into infinitesimally small points. In these extreme environments, you need both quantum mechanics and general relativity to describe what is happening. But the two theories refused to work together. It became clear that despite their individual successes, both theories must be incomplete. They must be approximations of some deeper truth that we had not yet discovered. Physicists needed a new theory that could unify all the different particles and forces of nature into one coherent framework. They needed a theory that could reconcile quantum mechanics with general relativity. They needed what came to be called a theory of everything, a single set of principles that could explain all physical phenomena from the smallest quantum particle to the largest structures in the cosmos. The search for this theory would lead to one of the most beautiful and controversial ideas in modern physics: the birth of string theory. The story of how string theory was born is one of those wonderful accidents that sometimes happen in science, where someone discovers the right answer while looking for something completely different. In the late 1960s, a young Italian physicist named Gabriele Veneziano was working on a very specific problem. He was trying to understand the strong nuclear force, which is the force that holds the nucleus of atoms together. This force is incredibly powerful, much stronger than electromagnetism or gravity, but it only works over extremely short distances. Veneziano was searching through mathematical formulas, looking for an equation that could describe how particles interact through the strong force. He was not working from any deep theoretical principle or physical insight. He was essentially trying different mathematical functions to see if any of them matched the experimental data that physicists had collected from smashing particles together in accelerators. Then he stumbled upon something remarkable. He found an old mathematical formula that had been discovered 200 years earlier by a Swiss mathematician named Leonhard Euler. This formula, called the Euler beta function, seemed to describe the strong force with astonishing accuracy. But here was the puzzling thing. The formula worked. It matched the experiments beautifully. But Veneziano had no idea why it worked. It was as if he had found the right answer to a test question, but could not show his work or explain his reasoning. The formula just seemed to drop out of pure mathematics with no physical interpretation behind it. This mystery tantalized physicists for several years. Then, in 1970, a physicist named Leonard Susskind, working at Stanford University, had a flash of insight that would change everything. He realized that the Veneziano formula made perfect sense if you stopped thinking about particles as tiny dimensionless points and instead imagined them as tiny, vibrating strings. This single conceptual shift from points to strings suddenly made everything fall into place. Think about a violin string for a moment. When you pluck a violin string, it vibrates back and forth, but it does not vibrate in just one way. If you pluck the string gently in the middle, you get a certain note, what musicians call the fundamental frequency. But the string can also vibrate in more complex patterns. It can vibrate in two halves, or 3 sections, or 4, producing what musicians call overtones or harmonics. Each different pattern of vibration produces a different musical note with its own distinct sound. Susskind proposed that the fundamental entities of nature work exactly the same way, except instead of being macroscopic objects you can see and touch, they are incredibly tiny strings vibrating at the quantum level. Each different pattern of vibration would appear to us not as a different musical note, but as a different particle. An electron would be one particular vibration pattern. A quark would be another vibration pattern. A photon, the particle of light, would be yet another vibration pattern. This idea was almost shockingly elegant and beautiful. Suddenly, all the different particles that physicists had catalogued, all those quarks and leptons and force carriers that seemed so random and arbitrary, could be understood as simply different notes played on the same fundamental instrument. Just as every song, every symphony, every musical composition that has ever existed or ever will exist can be created by playing different combinations of notes on a violin, every particle and force in nature could be understood as different vibrational modes of these fundamental strings. The implications were profound. We no longer needed to accept dozens of different fundamental particles as brute facts about nature. We no longer needed to say that electrons just happen to exist with exactly the mass and charge they have for no deeper reason. Instead, an electron had its particular properties because it corresponded to a string vibrating in one specific way, and that vibration pattern naturally and inevitably produced exactly the properties we observe. This was precisely the kind of unification that physicists had been dreaming about. It reduced the complexity of nature to something beautifully simple. One fundamental object, the string, vibrating in different ways to create the full richness and diversity of our universe. It was the kind of idea that Einstein might have appreciated, an idea where profound simplicity lurked beneath apparent complexity. But as physicists began to explore the mathematics of string theory more deeply, as they worked out the equations and followed the logic to its natural conclusions, they discovered something extraordinary. This theory came with implications that were so strange, so far beyond our everyday experience, that they seemed almost like science fiction. The price of this beautiful unification would be a radical reimagining of the nature of space, time, and reality itself. And that is where our journey is about to take us next. What strings are not? Before we can truly understand what strings might be made of, we need to be extremely clear about what they are not. This might seem like a strange place to start, but it is absolutely crucial, because the word string creates immediate associations in our minds, and almost all of those associations will lead us astray. When I say the word string, you probably immediately picture something. Maybe you think of a piece of thread, or a guitar string, or the string that ties a package. These are all completely natural associations, but every single one of them is wrong when it comes to understanding string theory. A violin string is made of something. It might be made of steel wire, or nylon, or catgut, which is actually made from sheep intestines. A thread you use for sewing is made of cotton or polyester fibers twisted together. A spider's silk is made of protein molecules that the spider produces in its body. In every case, when we encounter a string in everyday life, that string is composed of smaller things. It has substance, it has material. If you could look at it under a powerful enough microscope, you would see that it is built from molecules, which are built from atoms, which are built from particles. But the strings in string theory cannot possibly work this way. They cannot be made of atoms because atoms are supposed to be made of them. They cannot be made of quarks or electrons because quarks and electrons are supposed to be different vibration patterns of these strings. If strings were made of something smaller, then that smaller thing would be the truly fundamental entity, and we would have to ask what IT was made of, and we would be right back where we started. String theory proposes that strings are the end of the line. They are the most fundamental entities that exist. There is nothing smaller, nothing more basic, nothing underneath them. When we reach the level of strings, we have arrived at the ground floor of reality with no basement below. Now, let me give you another sense of just how different these strings are from anything in our everyday experience. The scale is almost impossible to comprehend. These strings are thought to be around the Planck length in size. The Planck length is about 10 to the power of minus 35 meters. To give you a sense of how small this is, imagine taking a single atom. An atom is already so small that you would need about 10 million of them lined up to span the width of the period at the end of this sentence. Now imagine that you could shrink down to atomic size, and from that perspective you look at a string. That string would appear smaller to you than an atom appears to us at our normal size. If we somehow enlarged an atom to be as big as the entire observable universe, stretching from one end of the cosmos to the other across billions of light years, a string in that scaled-up atom would still be only about the size of a tree here on Earth. The difference in scale is almost incomprehensible. At these dimensions, our normal everyday intuitions about matter and substance and what it means for something to exist completely and utterly break down. You might be wondering, if these strings are so impossibly small, how do we even know they exist? How can we talk about them with any confidence? This is an excellent question, and one that points to a deep issue in modern physics that we will return to later. For now, what is important to understand is that string theory is not based on direct observation of these strings. It is based on mathematical reasoning, on following the logic of physics to see where it leads, on discovering what kind of theory would be needed to solve the problems we discussed earlier. The mathematics of string theory is written in the language of mathematics, and the mathematics tells us something very specific and rather strange about what these strings are. According to the equations, strings have length, but they have absolutely zero thickness. They are what mathematicians call one-dimensional objects. Now, this might sound completely impossible. How can something exist in our universe but have no width whatsoever? How can something be infinitely thin and still be real? To understand this, we need to distinguish between mathematical objects and physical things in a way that might seem subtle but is actually quite important. Consider a line drawn on a piece of paper. In pure mathematics, when we talk about a line, we mean something that has length but absolutely no width. It extends in one dimension only. Of course, when you actually draw a line on paper with a pen or pencil, the ink or graphite that makes up that line does have width. You can see the width if you look closely. The physical mark on the paper is not a true mathematical line. But that does not mean the mathematical concept of a line is meaningless or useless. In fact, mathematical lines are incredibly useful for describing and predicting things in the real world. When engineers design a bridge, they use mathematical lines to represent beams and cables, even though the actual beams and cables have thickness. The mathematical idealization captures the essential features while ignoring details that are not important for the calculation. Strings in string theory are mathematical objects in a similar sense. They represent something in physical reality, but they exist at a level so fundamental that our usual concepts of material substance do not apply in the way they do for everyday objects. The mathematics describes strings as one-dimensional objects moving through space and time. As a string moves, it traces out a path through space-time, and that path forms what physicists call a world sheet. Imagine a string at one moment in time. It looks like a tiny loop or a tiny line segment. Now, as time passes, the string moves and vibrates. If you could somehow see the entire history of the string all at once, seeing all the positions it occupied at every moment in time simultaneously, you would see that it sweeps out a two-dimensional surface. This surface is the world sheet, and every calculation in string theory involves studying the properties and behavior of these world sheets. The mathematics of world sheets is actually quite beautiful and connects to many other areas of mathematics that were developed for completely different reasons. Physicists studying string theory have had to become experts in branches of mathematics like algebraic geometry and topology that were once considered purely abstract with no connection to physical reality. The fact that these mathematical tools turn out to be exactly what is needed to describe fundamental physics is something that many physicists find almost mystical, as if the universe is speaking to us in the language of pure mathematics. The equations tell us other things about strings as well. They tell us that strings have a property called tension, similar to how a rubber band has tension when you stretch it. This tension determines how the string vibrates and therefore what kinds of particles it can represent. The mathematics shows that this tension must be related to the Planck scale we mentioned earlier, which is why strings are so incredibly small. The equations also reveal that strings can be either open or closed. An open string is like a line segment with two ends. A closed string is like a tiny loop with no ends at all. Remarkably, closed strings vibrating in certain ways produce a particle that has exactly the properties of a graviton, the hypothetical particle that would carry the gravitational force in a quantum theory. This was actually not something that physicists put into string theory deliberately. It emerged naturally from the mathematics. When physicists discovered this, it was a moment of profound excitement because it suggested that string theory might naturally unify quantum mechanics with gravity, solving one of the deepest problems in physics without even trying. Energy and existence. Now we are beginning to approach the very heart of our central question. If strings are not made of anything smaller, if they are truly fundamental, then what gives them substance? What makes them real? What are they in the most basic sense? The answer that string theory offers is both simple and profound, but it requires us to think about energy in a new way. The answer is this: strings are made of energy. But we need to be very careful about what this means, because it is easy to misunderstand. In our everyday experience, energy is something that objects have, not something that objects are. A ball rolling down a hill has kinetic energy, energy of motion. A compressed spring has potential energy, stored energy waiting to be released. A battery has chemical energy. The sun radiates energy in the form of light and heat. In all these cases, energy seems to be a property of things, not the things themselves. But string theory, and really all of modern physics, is suggesting something more radical and more fundamental. At the deepest level of reality, the distinction between matter and energy dissolves. Energy does not just describe what things do. Energy is what things are. To understand this, we need to go back to one of the most famous equations in all of science, Albert Einstein's E = mc squared. Most people have heard this equation, but fewer people really understand what it means. Einstein discovered that energy and mass are not separate substances. They are two forms of the same underlying thing. Mass is simply concentrated energy. Energy is mass that has been released. The c in the equation stands for the speed of light. And because this speed is such an enormous number, and because we square it in the equation, this tells us that even a tiny amount of mass contains a tremendous amount of energy. This is why nuclear reactions release so much power. When an atomic nucleus splits in a nuclear reactor or fuses in the core of a star, a small amount of mass is converted into energy. And because of that c² factor, that small amount of mass becomes an enormous amount of energy. The bomb dropped on Hiroshima converted less than a gram of matter into pure energy, less than the mass of a dollar bill, but the result was devastation across an entire city. Einstein's equation told us that matter and energy are interchangeable. A particle with mass is really a concentrated knot of energy. An electron does not have mass and energy. An electron is a particular configuration of energy that manifests as mass. This was already a radical shift in how we think about matter, but string theory takes this insight and pushes it even further into more fundamental territory. In string theory, the strings themselves are pure energy, and the patterns of their vibration determine what kind of particle we observe. A string vibrating slowly in one pattern appears to us as an electron. A string vibrating more rapidly in a different pattern appears as a quark. A string vibrating in yet another way appears as a photon of light. The string itself is not made of electron stuff or quark stuff or photon stuff. The string is made of energy, and energy organized in different vibration patterns becomes these different particles. Think about ocean waves for a moment. A wave in the ocean is not made of water in the sense that the water molecules are permanently part of the wave. As a wave moves across the ocean, it is constantly made of different water molecules. The molecules move up and down as the wave passes, but they do not travel along with the wave. What moves is not the water itself, but a pattern of energy moving through the water. The wave is a traveling disturbance, a configuration of energy that exists temporarily in one set of water molecules, then moves on to organize different water molecules into the same pattern. String theory suggests that particles work similarly. They are not little chunks of stuff. They are patterns of vibration, configurations of energy that happen to be organized in a particular way. The string is the medium through which these patterns move, similar to how water is the medium through which ocean waves move. But unlike water molecules, which are themselves made of smaller things, strings are the ultimate medium. They are the most fundamental substrate of reality. But even this analogy breaks down because it still makes it sound like strings are things that contain energy, like water contains waves. The truth is more radical still. Strings do not contain energy. Strings are energy. There is no distinction. At this deepest level, energy and existence are the same thing. The quantum nature of strings. But there is yet another layer to this story, another aspect of what strings are that we need to understand. These strings exist in the quantum realm, where the rules are fundamentally different from anything in our everyday experience. Quantum mechanics, which we mentioned earlier as one of the great theories of 20th century physics, reveals that at very small scales reality works in ways that seem bizarre and counterintuitive to our everyday sensibilities. In the quantum world, everything has an inherent uncertainty and fuzziness built into it at the most fundamental level. You can never pin down both the position and the momentum of a particle with perfect precision at the same time. This is not because our measuring instruments are not good enough. It is not a limitation of our technology. It is a fundamental feature of how reality actually works at small scales. The more precisely you know where a particle is, the less precisely you can know how fast it is moving and in what direction. The more precisely you know its momentum, the fuzzier its position becomes. This uncertainty is described by Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics. But the strangeness of quantum mechanics goes even deeper than this. Particles in the quantum realm do not have definite properties until they are measured or observed. Before you measure an electron's position, it does not have a specific location. It exists in what physicists call a superposition, where it is in many different places simultaneously with different probabilities. Imagine flipping a coin but never looking at the result. In our classical everyday thinking, the coin lands as either heads or tails, and if you have not looked yet, you simply do not know which one it is. But the coin itself definitely is one or the other. Quantum mechanics says something much stranger. Before you look, the coin is not just unknown. It is genuinely both heads and tails at the same time, existing in a superposition of both states. Only when you look does it snap into being definitely one or the other. This is not just theoretical speculation. This has been tested in countless experiments and is confirmed every time. Particles really do behave this way. They exist in superpositions of multiple states until something interacts with them or measures them, and then they collapse into a definite state. This behavior is so counterintuitive that even Einstein, one of the founders of quantum mechanics, never fully accepted it. He famously said that God does not play dice with the universe. But experiments have proven again and again that at the quantum level, reality really does have this probabilistic, indefinite character. The strings of string theory are quantum objects through and through. They exist in this strange quantum realm where definite classical properties give way to probability clouds and superpositions. A string does not have one single definite shape or vibration pattern at any given moment. Instead, it exists in a quantum superposition where it simultaneously has many different configurations, many different vibration patterns all at once. Only when the string interacts with something else, only when it is in some sense measured or observed, does it snap into a particular state. This quantum nature is absolutely essential to understanding what strings are. They are not little solid objects in any classical sense. They are not tiny rubber bands floating in space. They are fundamentally quantum entities, which means they are more like clouds of possibility that become definite only through interaction. Their properties are probabilistic rather than deterministic. They embody the strange dual nature that quantum mechanics reveals, behaving sometimes like particles and sometimes like waves, or more accurately, being something that transcends both of these classical categories. When physicists calculate what happens when strings interact with each other, when strings collide or split apart or join together, they have to use the tools of quantum field theory. They cannot simply follow the strings along definite paths, as you might track billiard balls bouncing off each other on a pool table. Instead, they have to consider all possible paths the strings might take, all possible ways they might vibrate and interact, and then sum up the quantum amplitudes, the probability waves associated with each possibility. This process of summing over all possibilities is what gives string theory its predictive power, but also what makes it mathematically extremely complex and difficult to work with. The calculations involve advanced mathematics that can take years to master. But this complexity emerges naturally from the quantum nature of the strings themselves. They are not simple classical objects following deterministic paths. They are quantum entities exploring all possible configurations simultaneously until something pins them down into one particular outcome. Strings and space. Now we need to consider something even stranger, something that takes us into truly mind-bending territory. Throughout this entire discussion so far, we have been talking about strings moving through space, vibrating in space, existing at locations in space. This seems natural and obvious. Space is the stage, the empty container, the background in which everything else happens. Objects move through space. Events occur at locations in space, but space itself just sits there, unchanging, providing the arena in which the drama of physics unfolds. But string theory suggests something profoundly different. It suggests that space itself might not be fundamental. Space might not be the unchanging stage we think it is. Instead, space itself might emerge from something more fundamental, and that something might be the strings and their interactions. This is one of the most mind-bending ideas in all of modern physics, and it forces us to completely reconsider what we mean when we talk about space. To understand this idea, let us think about something familiar that emerges from more basic components. Think about temperature. When you feel warmth or cold, when you measure the temperature of your room with a thermometer, you are measuring something that seems real and fundamental. But temperature is not actually a fundamental property of matter. Temperature emerges from the motion of molecules. A hot gas is just a gas where the molecules are moving very rapidly, bouncing around frantically. A cold gas is one where the molecules are moving more slowly. Temperature is what we call an emergent property. It arises from the collective behavior of many particles, but is not a property of any single particle itself. Some versions of string theory suggest that space works the same way. Space is not a fundamental thing that exists on its own. Instead, space emerges from the relationships and interactions between strings. Imagine a vast network where the strings are the nodes, the connection points, and their interactions are the links between those nodes. The structure of this network, the pattern of how strings connect and interact with each other, creates what we experience as three-dimensional space. In this view, asking what strings are made of is a bit like asking what the internet is made of. The internet is not really made of anything in a material sense. The internet is a pattern of relationships between computers. It is the network of connections that allows information to flow from one place to another. The internet exists as an abstract structure built on top of physical hardware, but the internet itself, the network, is not a physical object. It is a pattern, a configuration, a web of relationships. String theory suggests that space might be similar. Space exists as a pattern of relationships between strings, not as a container that holds the strings. The strings do not exist in space. Rather, space is something that emerges from the strings and their interactions. This is an incredibly radical idea, because we normally think of space as the most fundamental thing there is. We think everything has to exist somewhere, has to have a location. But string theory is suggesting that location itself, and the space that defines locations, is a derived concept that only makes sense when you zoom out and look at the collective behavior of many strings. Another way to think about this is through an analogy with sound. Sound seems continuous to our ears. When you listen to music or hear someone speaking, you experience a smooth flow of sound waves. But at a deeper level, sound is not continuous. Sound is made of vibrations that travel through matter by making molecules bump into each other. In a sense, sound is not a fundamental feature of reality. Sound emerges from the collective behavior of particles pushing against each other. Some physicists think space works the same way. When we look at large scales, space appears smooth and continuous. We can move continuously from one location to another with no gaps or jumps. But at the tiniest scales, at the level of strings, space might not be continuous at all. It might be more like a digital computer image. When you look at a photograph on a computer screen from far away, it looks smooth and continuous. But if you zoom in close enough, you see that the image is made of discrete pixels, individual dots of color arranged in a grid. The smoothness is an illusion that emerges when you have enough pixels close together. Space might emerge from strings in a similar way. At the Planck scale, at the level of strings, space might not exist in the smooth, continuous way we experience it. Only when you look at the collective behavior of vast numbers of strings does this thing we call space emerge. The implications of this idea are staggering. It means that everything we think we know about space, all our intuitions about distance and location and dimension, only apply at scales much larger than the fundamental scale. At the deepest level, reality might work in completely different ways. The role of time. Just as string theory challenges our understanding of space, it also forces us to completely reconsider time. In our everyday experience, time flows forward inexorably from past to future. We remember the past, but not the future. We can influence the future, but not the past. This arrow of time seems like one of the most fundamental features of reality. But quantum mechanics and string theory suggest that time, like space, might be an emergent phenomenon rather than something fundamental. Albert Einstein's theory of relativity showed us that space and time are not separate things, but are woven together into a single unified fabric called space-time. Events do not happen in space at a time. They happen at locations in space-time, and different observers moving at different speeds will disagree about when and where events occur. There is no absolute time that ticks away the same for everyone in the universe. Time is relative and depends on motion and gravity. But string theory suggests we might need to go even further in rethinking time. Some formulations of string theory do not assume time exists from the start. Instead, they begin with mathematical equations that describe relationships and structures, and time emerges from those relationships under certain conditions, similar to how space emerges from the interactions of strings. To understand this strange idea, think about a movie. When you watch a film, you experience a smooth flow of motion and change unfolding before your eyes. You see characters moving, speaking, acting. You see events happening in sequence, one after another. The passage of time seems real and fundamental to the experience. But if you look at the physical film itself, or at the digital file that contains a movie, you see something very different. A film is just a series of still images, individual frames that do not move at all. Motion and time emerge when these static frames are played in rapid sequence. The flow of time you experience is not actually in the film itself. It emerges from the way the frames are organized and presented. Some physicists think fundamental reality might work in a similar way. What we experience as the flow of time, as the continuous march from past to future, might emerge from something more fundamental, that does not itself involve time. At the deepest level, there might just be mathematical relationships and structures, and time becomes something that appears when you look at those structures in a certain way or at a certain scale. This raises a fascinating question about strings. Do strings vibrate in time, or does time emerge from their vibrations? Is the vibration of strings something that happens as time passes, or is the passage of time itself a consequence of strings vibrating? These questions sound almost like philosophical word games, but they point to something deep about the nature of reality that physicists are still grappling with. The mathematics of string theory can be formulated in ways that do not assume time exists from the beginning. Physicists can write down equations that describe the structures and relationships of string theory in a timeless way, and then show that under certain conditions, something that looks and behaves like time emerges from those equations. It is as if time is not written into the fundamental laws of physics, but instead is something that emerges when the universe is in certain states or configurations. If this is true, it means that our everyday experience of time flowing from past to future, while completely real at our scale, is not capturing something fundamental about reality at the deepest level. Just as temperature is real and measurable but emerges from molecular motion, time might be real and measurable but emerge from more fundamental timeless structures. Our entire lives, everything we experience as happening in sequence, might be like frames of a film that all exist simultaneously at some deeper level of reality. This is admittedly extremely difficult to wrap our minds around because we are so deeply embedded in time. Every thought we have, every perception, every memory is structured by time. Asking us to imagine reality without time is like asking a fish to imagine what it would be like to live outside of water. But the mathematics of string theory and quantum gravity suggests this might be necessary to understand the ultimate nature of reality. Extra dimensions. Now we come to one of the most famous and most bizarre features of string theory, something that has captured the imagination of scientists and science fiction writers alike. The mathematics of string theory only works consistently, only produces sensible answers without contradictions, if space has more than the 3 dimensions we experience in everyday life. Depending on which version of string theory you are working with, space needs to have 9 or 10 spatial dimensions plus time, for a total of 10 or 11 dimensions of space-time. This seems absolutely absurd on the face of it. We live in a 3-dimensional world. We can move forward and back, left and right, up and down. These are our 3 dimensions of space. We cannot move in any other spatial direction because there are no other spatial directions to move in. So where could these extra 6 or 7 dimensions possibly be hiding? How can space have dimensions we never experience? The answer that string theory provides is both ingenious and strange. The extra dimensions are curled up incredibly small, so small that even at the scale of individual particles, we cannot detect them. To understand this, think about a garden hose lying on the ground some distance away from you. If you look at the hose from far away, it looks like a one-dimensional line stretching from one point to another. you see only length. But imagine you are an ant crawling on the surface of that hose. To you, the hose is not one-dimensional at all. You can move along the length of the hose, but you can also move around the circumference of the hose. From your perspective on the surface, the hose has two dimensions. One dimension is large and obvious, stretching for meters or more. The other dimension is wrapped around in a tiny circle that repeats every few centimeters as you go around the hose. String theory proposes that something similar happens with the dimensions of space, except at a much smaller scale. We experience three large extended dimensions that stretch across billions of light-years of space. But at every single point in these three dimensions, there are additional dimensions curled up into tiny shapes so small that we cannot detect them. These curled-up dimensions might have complicated geometries folded and twisted in intricate ways, but they are all confined to scales near the Planck length, the same scale at which strings themselves exist. Now, here is where this becomes truly important for understanding strings. The way these extra dimensions are curled up, the specific shape they are curled into, determines what kinds of vibrations the strings can have. Think about musical instruments again. A violin string and a guitar string can both play notes, but they sound different because of the different shapes and sizes of the instruments. The body of a violin has a different shape than the body of a guitar, and this affects which vibrations resonate and which are damped out. Similarly, strings vibrating in space-time will have different possible vibration modes depending on the geometry of the extra dimensions. A string wrapping around one of these tiny curled-up dimensions will be affected by the shape and size of that dimension. Different shapes for the extra dimensions will allow different sets of vibrations, which means they will produce different sets of particles. The specific particles we observe in our universe, with their specific masses and charges and other properties, are determined by the geometry of these hidden extra dimensions. This is why string theorists spend so much time studying different possible shapes for the extra dimensions. These shapes are called Calabi-Yau manifolds, named after two mathematicians who studied their properties. There are many possible Calabi-Yau manifolds, possibly infinitely many, and each one would produce a different universe with different particles and forces. Finding which Calabi-Yau manifold, if any, corresponds to our actual universe is one of the major unsolved problems in string theory. But here is something even more mind-bending. These extra dimensions are not somewhere else. They are not in some parallel universe or alternate dimension in the science fiction sense. These extra dimensions are right here, at every single point in space that you can see and touch. Right now, as you exist at this moment, you are not just at a location in three-dimensional space. You are at a location in 9 or 10-dimensional space. 6 or 7 of those dimensions are curled up so tightly that your entire body, every atom in your body, is effectively smeared across all the possibilities in those tiny dimensions. You exist in all these extra dimensions, but they are so small you have no way to perceive them. If we could somehow magnify a point in space, zooming in past atoms, past particles, down to the Planck scale, we would see that what looks like a simple point is actually a rich, multidimensional structure. Each point would reveal itself to have this elaborate hidden geometry, these extra dimensions curled up in complex shapes. It would be like discovering that every pixel on a computer screen actually contains an entire world of structure invisible at normal resolution. The existence of these extra dimensions has profound implications for what strings are. Strings do not just exist in our familiar 3 dimensions, they exist in this full, higher dimensional space. They can vibrate in these extra dimensions. They can wrap around the extra dimensions multiple times, like thread wrapped around a spool. All of this affects what properties the strings have and what kinds of particles they produce when we observe them in our 3-dimensional slice of reality. So, after all this exploration, after traveling through quantum mechanics and relativity, through extra dimensions and emergent space-time, we can finally return to our original question with a deeper understanding. What are strings made of? The answer that most string theorists would give today is this. Strings are not made of anything more fundamental. They are the fundamental entities. But as we have seen, this answer requires very careful interpretation because it means something quite different from what we might initially think. Strings are not material objects in the traditional sense. They are not little pieces of stuff that have substance and weight and solidity. When we ask what strings are made of, we are asking a question that assumes material composition, assumes there are building blocks, assumes reality works like Lego bricks, where everything is constructed from smaller pieces. But string theory is telling us that at the most fundamental level, reality does not work this way at all. Strings are better understood as excitations in quantum fields, or as patterns in the mathematical structure that underlies reality, or as vibrating concentrations of energy. They are made of the same stuff that space, time, and energy are made of, which is to say, they are not made of stuff at all in any conventional sense. At this deepest level, the distinction between matter and energy, between substance and form, between thing and process, completely breaks down. Think about an ocean wave again. What is a wave made of? You might say water, but as we discussed earlier, the water molecules do not travel with the wave. They just move up and down as the wave passes through. The wave is not really made of water. It is made of energy, organized into a particular pattern moving through water. But even saying the wave is made of energy is not quite right. The wave is a pattern of energy. It is energy configured in a certain way. The wave and the energy are not two separate things where one is made of the other. They are two ways of describing the same phenomenon. Strings are similar. They are patterns in the quantum fields that fill all of space. They are vibrations in the fundamental fabric of reality. They are mathematical structures that have physical consequences. At this level, these descriptions start to mean the same thing. The distinction between physical and mathematical, between real and abstract, becomes blurry because we have reached a level so fundamental that our language and concepts start to break down. Strings have properties like tension. the ability to vibrate, the capacity to interact with other strings. But these properties do not come from strings being composed of something else that gives them these properties. These properties are intrinsic to what strings are. They are built into the mathematical structure of string theory itself. Asking why strings have tension is like asking why circles are round. It is part of the definition, part of what makes them what they are. In the mathematics of string theory, there is a fundamental constant that determines the tension of strings. This is related to the Planck length and the strength of quantum gravity. This constant is not derived from anything more fundamental. It is one of the input parameters of the theory, something you have to put in by hand based on observations of our universe. The fact that strings have exactly this tension and not some other value is ultimately a fact about our universe that string theory accepts as given rather than explains. What string theory does explain is how given strings with this particular tension vibrating in space-time with extra dimensions curled up in particular ways, all the particles and forces we observe naturally emerge. It explains how the richness and complexity of our universe, with all its diverse particles and elaborate forces, can arise from this simple foundation. It shows how quantum mechanics and gravity can fit together in a consistent mathematical framework. It provides a potential answer to how all of reality hangs together as a coherent whole. But the question of what strings themselves ultimately are, what gives them existence, what grounds them in reality, remains in some sense unanswered. Or perhaps it is better to say that the answer is that this is as far as explanation can go. Strings are the fundamental entities, and asking what they're made of is asking for a kind of explanation that cannot exist. It would be like asking what exists outside the universe, or what happened before time began. The question assumes there is a further level of reality to appeal to, but if strings are truly fundamental, there is no such level. Different string theorists might frame this somewhat differently. Some emphasize that strings are quantum excitations of fundamental fields. Others emphasize that strings are mathematical structures whose reality consists in their ability to organize our observations and predictions. Others focus on strings as patterns of energy and information. But all of these perspectives converge on the same basic insight. At the deepest level, reality is not made of stuff in any ordinary sense. It is made of relationships, patterns, mathematical structures that manifest as the physical world we observe. The problem of proof string theory has been developed and refined over more than 50 years now. Thousands of the world's brightest physicists and mathematicians have dedicated their careers to working out its implications. The theory has led to beautiful and profound mathematics, to surprising connections between different areas of physics and mathematics that nobody expected, to deep insights about the nature of space and time and quantum mechanics. But there is a significant and troubling problem that has hung over string theory from the beginning and remains unresolved today. We have no experimental evidence that strings actually exist. This might seem shocking given everything we have discussed. How can physicists spend decades working on a theory, writing thousands of papers, building entire careers around an idea, when they have no direct evidence that the fundamental objects in the theory are real? The issue comes down to the scales involved. We talked earlier about how incredibly tiny strings are supposed to be, about the Planck length, and the vast gulf between the size of strings and the size of anything we can currently detect or measure. To directly observe strings, to see them vibrating or interacting, we would need to probe nature at energy scales far beyond what any particle accelerator can achieve. The Large Hadron Collider, the most powerful particle accelerator ever built, which cost billions of dollars and took decades to construct, can probe down to scales of about 1/10,000, the size of a proton. This is incredibly small, small enough to discover new particles like the Higgs boson and to test the standard model of particle physics with exquisite precision. But strings are predicted to exist at scales trillions upon trillions of times smaller than what even the Large Hadron Collider can reach. To build a particle accelerator powerful enough to directly detect strings, we would need a machine larger than our entire solar system, perhaps larger than our galaxy. This is obviously completely impractical, utterly beyond any conceivable technology for the foreseeable future. So we cannot test string theory through direct observation of strings themselves. Now, string theory does make some predictions that could, in principle, be tested without directly seeing strings. It predicts certain relationships between particles, certain symmetries, certain behaviors at high energies. The problem is that most of these predictions are either extremely vague or occur only at energies we still cannot reach. Some versions of string theory predict extra particles called superpartners that should exist at energies accessible to the Large Hadron Collider. Physicists have searched intensively for these particles, but so far they have not found them. This does not definitively rule out string theory, because maybe the superpartners are just slightly heavier than we can currently detect. Or maybe the particular version of string theory that predicts them at accessible energies is not the right version. But it does mean that string theory has not yet made a clear prediction that has been tested and confirmed by experiment. For many physicists, this is a serious problem. Science is supposed to be based on the interplay between theory and experiment. You develop a theory, the theory makes predictions, you test those predictions, and the results either confirm or refute the theory. String theory seems to exist in a strange limbo where the theory is so far removed from experimental verification that we cannot complete this cycle. This raises profound questions about the nature of science itself. If a theory is mathematically beautiful and internally consistent, if it solves deep theoretical problems and provides satisfying explanations, if it connects different areas of physics in surprising ways, but it cannot be tested experimentally, is it really physics? Or has it crossed over into being pure mathematics or even philosophy? Different scientists give different answers to this question. Some argue that string theory should be judged primarily on its mathematical elegance and its ability to solve theoretical problems, even without experimental confirmation. They point out that many great theories in the history of physics, including Einstein's general relativity, were initially accepted largely because of their mathematical beauty and explanatory power, with experimental confirmation coming later. They argue that string theory deserves the same consideration. Others are more critical. They worry that without the constraint of experimental testing, theoretical physics might drift away from reality into mathematical fantasy. They point out that there are many mathematically consistent theories that have no connection to the actual universe we live in. How do we know string theory is not just beautiful mathematics that happens to have no relevance to physical reality? Without experiments to guide us, how do we know we are on the right track? This debate has sometimes become heated, with accusations that string theory has absorbed too much talent and resources, that young physicists feel pressured to work on string theory even if they are skeptical because that is where the jobs and prestige are, that the field has become somewhat insular and resistant to criticism. These are serious concerns about the sociology and practice of science, regardless of whether string theory itself ultimately turns out to be correct. Alternative theories, because of these challenges with string theory, and also simply because scientists like to explore different ideas and not put all their eggs in one basket, various physicists have pursued alternative approaches to the same fundamental problems that string theory attempts to solve. These alternative theories take very different starting points and lead to very different pictures of what fundamental reality looks like. It is worth exploring some of these alternatives to understand the landscape of ideas and to see that string theory, while prominent, is not the only game in town. One of the most developed alternatives is called loop quantum gravity. This approach takes a very different philosophical starting point from string theory. Instead of trying to unify all forces and particles into one framework as string theory does, loop quantum gravity focuses more narrowly on trying to make gravity work with quantum mechanics. And instead of replacing particles with strings, loop quantum gravity proposes that space itself is quantized at the smallest scales. In loop quantum gravity, space is not smooth and continuous, even at the Planck scale. Instead, space is made of tiny, discrete chunks, quantum units of volume that are connected together in a network that looks something like a spider web or a chain-link fence at the smallest scales. These connections between chunks of space are the loops that give the theory its name. They form closed curves in space, and the quantum state of space is described by how these loops are arranged and connected. In this picture, particles are not fundamental objects. Particles are excitations or disturbances in this quantum network of space. An electron or a quark is a particular pattern of how these loops of space are linked together, similar to how a knot in a rope is not made of some different material, but is just the rope configured in a particular way. Matter emerges from the structure of space rather than existing separately within space. Loop quantum gravity has some advantages over string theory. It does not require extra dimensions. It works in the familiar 3 dimensions of space plus time. It makes some specific predictions about what happens at very high energies that differ from string theory's predictions, although these predictions are still beyond our current ability to test. The theory has been developed rigorously and has attracted a dedicated community of researchers. However, loop quantum gravity also has limitations. It has not succeeded in unifying gravity with the other forces the way string theory attempts to do. It describes quantum gravity but does not provide a complete theory of all particles and interactions. It is less ambitious in scope than string theory, focusing on a narrower set of problems. Whether this makes it more realistic and achievable or less complete and satisfying depends on your perspective. Another interesting alternative approach is called asymptotic safety. This is based on a different idea entirely. Maybe we do not need strings or loops or any exotic new structure. Maybe gravity and quantum mechanics can be made compatible without adding anything fundamentally new, if certain mathematical properties of gravity work out in a particular way at extremely high energies. The idea is that while gravity seems incompatible with quantum mechanics at first glance, as we discussed earlier with the infinities that appear in calculations, maybe those infinities are an artifact of how we are doing the calculation rather than a real problem with combining the theories. If the strength of gravity changes in just the right way as you go to higher and higher energies, then the problematic infinities might cancel out or become manageable. Gravity would become what physicists call asymptotically safe, meaning it approaches a safe, stable state at high energies rather than blowing up to infinity. This is an elegant idea because it would mean that general relativity and quantum mechanics might work together without needing any dramatic revolution in our understanding of space, time, or matter. We would not need strings or extra dimensions or quantized space. We would just need gravity to have certain mathematical properties that, while not obvious, are at least conceivable. However, it remains unclear whether asymptotic safety actually works for gravity. The calculations are extremely difficult and results are not yet conclusive. Beyond these specific proposals, there are various other ideas being explored by smaller groups of researchers. Some physicists work on theories where time is more fundamental than space, or where information is the most fundamental substance. Some explore ideas from mathematics about non-commutative geometry, where the order in which you do things matters even at the level of coordinates and locations. Some investigate whether space-time might emerge from networks of quantum entanglement, the spooky connections between distant particles that Einstein found so troubling. What all these alternatives show is that the problem of quantum gravity and fundamental physics remains open. String theory is the most developed and widely explored approach, but it is not proven, and there are other ideas with different strengths and weaknesses. This is actually healthy for science. Having multiple competing approaches helps prevent any single idea from calcifying into dogma. It ensures that different possibilities are explored and that we do not miss promising avenues by focusing too narrowly on one approach. Strings within strings. Even within string theory itself, the picture has become considerably more complex and richer than the simple idea of vibrating strings that we started with. As physicists explored the mathematics of string theory more deeply throughout the 1980s and 1990s, they discovered that the theory contained much more than just strings. There are higher dimensional objects called branes, pronounced like membranes, that play crucial roles. The name brain is deliberately evocative of membrane, and indeed a two-dimensional brain is essentially a membrane, a flexible sheet that can curve and vibrate. But brains can have different numbers of dimensions. There are zero-dimensional brains called D0 brains, which look like particles from far away. There are one-dimensional brains, which are strings themselves. There are two-dimensional brains, which are membranes. There are three-dimensional brains, four-dimensional brains, and so on. In theories with 10 total dimensions, you can have brains with up to 9 spatial dimensions. These brains are not separate objects that were artificially added to string theory. They emerged from the mathematics when physicists studied certain equations carefully. They discovered that the equations of string theory naturally contained solutions describing these higher dimensional objects. The brains were hiding in the theory all along, waiting to be discovered. This is one of those remarkable features of string theory that its supporters find compelling. The theory keeps revealing unexpected richness as you explore it more deeply. One of the most intriguing ideas involving brains is that our entire observable universe might be a three-dimensional brain floating in a higher dimensional space. All the particles and forces we experience, all the matter and energy we can detect, might be confined to this three-dimensional brain, while gravity can leak off into the extra dimensions. This is called the brain world scenario, and it was developed extensively in the late 1990s and early 2000s. In this picture, we are not directly aware of extra dimensions because we are stuck on our brain, like ants crawling on a sheet of paper floating in a three-dimensional room. We can move freely in the three dimensions along our brain, but we cannot move off into the extra dimensions that exist in the room. However, gravity is different. Gravity might be able to spread out into all the dimensions, not just the three we are confined to. This could explain why gravity is so much weaker than the other forces. The gravitational force might be diluted by spreading into dimensions we cannot access. This brain world idea led to testable predictions about how gravity might behave differently at very small distances, and experiments have looked for these effects, although so far without finding them. But what is more important for our current discussion is what this means for understanding what is fundamental. If there are brains as well as strings, which is more fundamental? Are strings the basic objects and brains are made of strings, or are brains equally fundamental? The answer seems to be that in some sense they are all equally fundamental, or perhaps better to say they are all different aspects of the same underlying theory. This realization came from a series of discoveries in the mid-1990s that revolutionized string theory. Physicists found that there were actually 5 different consistent versions of string theory, each with slightly different properties and different numbers and types of brains. At first, this seemed like a problem. Which version was the correct theory of our universe? But then physicists discovered something remarkable. These 5 different theories were not actually different theories at all. They were 5 different mathematical descriptions of the same underlying theory. 5 different perspectives on one unified structure. They were related by dualities, mathematical transformations that showed that what looked like a string in one version looked like a brain in another version. What looked like weak interactions in one version corresponded to strong interactions in another version. The 5 theories were like 5 different maps of the same territory, each emphasizing different features, but all describing the same underlying reality. This suggested that there must be some more fundamental theory from which all 5 string theories emerge as special cases. Physicists gave this hypothetical underlying theory a name. They called it M-theory. The M might stand for membrane, or mother, or mystery. Different physicists have offered different interpretations, but M-theory represents the idea that strings and all the different types of brains are different manifestations of something even deeper. What that deeper something is remains mysterious. M-theory is still not fully understood or fully formulated. We have glimpses of it, pieces of the puzzle, mathematical hints, but not yet a complete picture. Some physicists have suggested that M-theory might involve yet more fundamental objects, perhaps involving pure information or mathematical structure in ways we have not yet grasped. The question of what strings are made of thus becomes even more complex. Perhaps strings are not the most fundamental objects after all. Perhaps they are themselves emergent phenomena arising from the more fundamental structures of M-theory. The nature of reality. Our journey through string theory and its implications brings us finally to profound questions about the nature of reality itself. For thousands of years, going back to the ancient Greek philosophers we mentioned at the very beginning, human thought has been dominated by a certain assumption about how the world works. We have assumed that matter is the fundamental substance of the universe. We have built our entire worldview around the idea that the universe is made of stuff, of things, of objects that exist in space and time with definite properties and characteristics. This materialism, as philosophers call it, seems like common sense. When you pick up a rock, it feels solid and real. It has weight and texture and temperature. It seems obvious that the rock is made of matter, of substance, of stuff that simply exists in some fundamental sense. Our language is built around this assumption. We talk about things and objects and substances. We describe the world in terms of nouns, entities that have being. But modern physics, culminating in string theory, but really beginning with quantum mechanics and relativity, suggests something radically different. At the deepest level that we can probe, reality might not be made of stuff at all. It might be made of mathematical relationships, patterns of information, pure structure with no substance underlying it. This is not easy to accept or even to fully comprehend, because it goes against every intuition we have developed through our everyday experience with the world. Think about what we have learned in our exploration. We have seen that particles, which we normally think of as little chunks of matter, are better understood as patterns of vibration in quantum fields or as excitations of fundamental strings. We have seen that these strings themselves are not made of any material, but are better understood as concentrated knots of energy or mathematical structures in a quantum theory. We have seen that even space and time, which we think of as the most basic features of reality, might themselves emerge from more fundamental structures rather than being fundamental themselves. At each level, as we dig deeper, the material substance we thought was there seems to dissolve into something more abstract, more mathematical, more like pure form than like matter. It is as if reality is made of the patterns themselves rather than of some substance that takes on those patterns. This is a bit like a song. What is a song made of? A song is not made of the paper that music is written on, nor the air vibrations when it is played, nor the electromagnetic patterns when it is transmitted over radio. The song is the pattern, the structure, the information, and that pattern can be embodied in many different physical substrates without changing what the song fundamentally is. String theory suggests that fundamental physical reality might work similarly. The patterns, the mathematical structures, the relationships might be what is truly fundamental, and what we call matter or energy or particles are just these patterns manifesting in ways that we can observe and measure. The equations of string theory are in a sense more real than the physical phenomena they describe, because the physical phenomena are derived from the equations rather than the other way around. This should not be too surprising when we think carefully about it. We have known since quantum mechanics that particles can behave as waves, that they do not have definite properties until measured, that they exist in superpositions of multiple states. We have known since relativity that matter and energy are interchangeable, that mass is just concentrated energy. We have known that particles can be created from pure energy and can annihilate back into energy. The idea that there are little balls of solid stuff bouncing around has been untenable for more than a century. String theory is simply the next step in this progression away from naive materialism toward a more abstract and mathematical understanding of reality. When we ask what strings are made of, we are perhaps asking the wrong kind of question. We are asking a question that assumes reality must be made of something, that there must be substance at the bottom. But string theory suggests that substance is itself an emergent concept, something that appears at certain scales and under certain conditions, but is not present at the most fundamental level. This has deep implications for philosophy and even for how we think about ourselves. If matter is not fundamental, if the universe is fundamentally mathematical structure rather than material stuff, what does that mean for consciousness, for human existence, for the nature of mind? These questions go beyond physics into philosophy and metaphysics, but they are questions that string theory naturally raises by challenging our assumptions about what reality is made of. As we reach the end of our exploration, we can step back and reflect on what we have learned and what remains to discover. The question of what strings are made of has taken us on a remarkable journey through some of the strangest and most beautiful ideas in modern science. We have traveled from the ancient Greeks wondering about atoms, through the discovery of quantum mechanics and relativity, into the realm of strings vibrating in 10-dimensional space, to questions about whether space and time themselves are fundamental or emergent. We have seen that at the deepest level we can currently probe the familiar categories that organize our everyday experience, categories like matter and energy, space and time, substance and property, all begin to blur together and lose their distinct meaning. We have encountered the possibility that our three-dimensional world is just a slice of a higher dimensional reality, that extra dimensions might be curled up at every point in space, too small for us to detect. We have grappled with the idea that reality at its foundation might be mathematical structure rather than physical substance. String theory itself remains unproven, and it may ultimately turn out to be wrong. Perhaps loop quantum gravity will prove correct instead. Perhaps asymptotic safety will resolve the problems of quantum gravity without needing any exotic new structures. Perhaps some theory that has not yet been conceived will emerge and eclipse all current approaches. This uncertainty is not a weakness of science, but a strength. It shows that science remains open, that physicists are honestly grappling with deep problems whose solutions are not yet known. But regardless of whether string theory in its current form turns out to be correct, the questions it raises are valuable and important. These questions push us to think more carefully and more deeply about what we mean by fundamental, about what it means for something to exist, about the relationship between mathematics and physical reality, about the ultimate nature of space and time and matter. Wrestling with these questions expands our conception of what is possible, of what reality could be like at its deepest levels. The next generation of physicists and mathematicians will continue this quest. They will have better mathematical tools, more sophisticated computational abilities, perhaps new experimental techniques that we cannot yet imagine. They may find ways to test string theory's predictions that seem impossible today. They may discover connections between string theory and other areas of physics or mathematics that provide new insights. They may reformulate the theory in ways that make it more tractable or more clearly connected to observable phenomena. Or they may abandon string theory entirely and pursue completely different approaches. Science progresses not in straight lines, but through exploration of many paths, some of which lead to dead ends, while others open up new vistas. What matters is that we continue asking deep questions and following the logic of mathematics and experiment wherever they lead, even into strange and unfamiliar territory. The question of what strings are made of is really a question about the ultimate nature of reality. It is a question about what exists at the deepest level, about what grounds and supports everything else. It is, in some sense, the oldest question in philosophy and science, the question that Democritus and the ancient Greeks asked when they wondered, what would happen if you kept cutting matter into smaller pieces? What do you reach at the end? What is the foundation? String theory's answer is that you reach vibrating strings of pure energy existing in a quantum superposition in 10-dimensional space-time, where space and time themselves might be emergent from more fundamental structures, and where the strings are not made of anything but simply are the fundamental entities. This answer raises as many questions as it answers, but that is exactly what a good scientific theory should do. It should deepen our questions even as it resolves old puzzles. As we continue to peer deeper into the foundations of reality, we are not just discovering what the universe is made of in some narrow technical sense. We are discovering new ways of thinking about existence itself, about what it means for anything to be real, about the relationship between the abstract world of mathematics and the concrete world of phenomena that we experience. We are learning that reality is stranger, more subtle, more wonderful, and more deeply mathematical than we ever imagined. The ancient Greeks began this journey by asking what matter is made of. Thousands of years later, we are still on that same journey, though it has taken us to places they could never have anticipated. We have discovered that the question itself needs to be reformulated, that matter is not fundamental, that composition and substance are not the right concepts at the deepest levels. We have learned that reality is structured more like music than like machinery, more like mathematics than like matter. And yet the journey continues. String theory is not a final answer, but a waypoint, one stage in an ongoing exploration that may never truly end. Each answer we find opens up new questions. Each layer we peel back reveals new depths beneath. This is the nature of fundamental physics, and perhaps the nature of human understanding itself. We are always reaching towards something deeper, something more fundamental, something that will finally explain everything. Whether we will ever reach that ultimate explanation, whether there even is a final theory of everything, or whether reality has infinite layers going down forever, remains unknown. But the search itself, the journey of exploration and discovery, the gradual unveiling of nature's deepest secrets. This is one of the most profound and meaningful endeavors that human beings have ever undertaken. And every person who takes the time to understand these ideas, to grapple with these questions, to wonder about what strings are made of and what that means, becomes part of that ancient and ongoing quest to understand the cosmos and our place within it. This is where our exploration must end for now, but the questions remain. What are strings made of? What is the ultimate nature of reality? These questions will continue to inspire and perplex future generations, just as they have inspired and perplexed us today. And perhaps someday, armed with new mathematics and new insights and new ways of thinking about these deep problems, humanity will find answers that we can only dimly imagine today. That possibility, that hope, is what drives science forward into an unknown but endlessly fascinating future.